delay is coming in the afternoon, not in the morning, but after a successful presentation in NASA, hopefully you guys are going to have the same strength. Ready to go whenever you guys are ready.
All right. Thank you all for coming out here today. We are KST6, and our project is the design and manufacturing of a heat exchanger using thermal reutilization of an oxygen supply system. My name is Samuel Ogletree. Additional team members are Sean Lee, Shannon Mohammed, Alejandro Ruiz, and Tyler Young. In this presentation, we will discuss the need for our design evolution, our experimental results and analysis, and our cost analysis. So historically, small-scale oxygen supply systems have been costly and inefficient to operate. However, a new technology that you can see here on the right, called the ceramic transport membrane, has the potential to address these issues. The system works by introducing atmospheric air that has been preheated by a heating element into the cathode channel, coming in contact with the porous cathode electrode, where a chemical reaction takes place, reducing carbon dioxide to carbon monoxide and oxygen. So the oxygen produced by this chemical reaction, as well as any other oxygen in the atmosphere, is then transported through the central electrolyte membrane and into the anode channel. The deoxygenated hot exhaust remaining in the cathode channel is vented from the system, and the oxygen supplied to the anode channel can then be transported for storage or use. So in its current form, this system consumes more power than alternative methods. And this is largely due to the heat losses associated with the hot exhaust from the cathode channel, as well as the oxygen supplied by the anode channel. So in order to address this issue, our project objective is to develop a heat exchanger that utilizes that hot exhaust energy to preheat the incoming atmospheric air in order to reduce the power consumption of the heating elements. To discuss more about the design constraints and considerations of this project, Sean.
Thank you, Sam. Now, before we can begin on our design, we must first consider its design constraints. As Sam has put out earlier, this overall system had one major constraint, the 800 degrees Celsius exhaust temperature. Normally, heat exchangers are made out of copper or aluminum, which has very high thermal conductivity, but at these temperatures, you're looking at very weak structures. So we had to look towards a weaker, less thermal conductive materials such as steel, stainless steel, and carbon steel. The second constraint that we had was a very low flow rate through these CTM. At 20 SLPM, when you calculate it out, it comes out to barely 0.03 kilogram per second as a mass flow rate. This hampers the amount of heat that can be transferred throughout the entire system. In addition to these two system constraints, we also had a locational constraint. On utilization on Earth, these CTMs are to be delivered in remote areas, such as clinics, remote clinics, and emergency areas. In these cramped conditions, cost effectiveness becomes a major part because they don't have the budget to afford more expensive equipment, and thermal safety becomes a major issue. You can have a patient accidentally touching the CTM and be burned. As we move on, this is how our heat exchanger goes into the thermal system. As you can see, the hot 800 degrees exhaust comes into the heat exchanger, which then preheats the atmospheric air to a higher temperature, which we can then feed into the heater. This heater now takes less power than the previous one, and we can save power and make it safer. Moving on to research and development. In this case, we constructed a view chart by looking at 6 different types of heat exchanger, ranging from the common double pipe heat exchanger to a shell and tube heat exchanger. Their strengths and weaknesses are tallied upon here, and we focus more upon the heat transfer and pressure drop. After our research area, we can see that the double pipe heat exchanger and the shell and tube heat exchanger came out on top. Each has their advantages, and each has one major disadvantage. For the double pipe heat exchanger, it had very excellent thermal transfer, but as it gets larger to hit the 800 degrees mark, the pressure drop becomes unacceptable. We're pushing more power through the fans than the power that is saved. For the shell and tube heat exchanger, this one had less heat transfer, but it had an acceptable pressure drop. So for us, we decided to combine these two designs into a single one and then produce a prototype out of it. To talk more about this, we have Sean Mohammed.
Thank you, Sean. So for our design, our basic design, we knew we wanted a shell and tube type heat exchanger because they would be easier to fabricate, and we wanted it to have a counterflow configuration, which would yield the most heat transfer. To start off, we had HX0, our initial design, this one right here. It had 4 tubes making 6 bends and multiple baffles. The shell material was made out of 1010 carbon steel, and the tube was bent using soft copper piping. We learned a great deal from both the fabrication and the testing. What we learned was that we had a low pressure drop, that we wanted to get rid of the tube bending as it was really hard to work around during fabrication, and most importantly, we had to be more lenient with our drawing tolerances. So when we did fabricate the pieces, they would fit better. Utilizing what we learned, we designed and fabricated HX1, this testing design, this one right here in the middle. We made this to be modular. We made it out of 304 stainless steel, and we made the tubes to be larger in diameter, so the areas are closer together. We designed this, like I said, to be modular, as the top comes right off. We could put in more baffles, take out baffles, and do different tests on it to see what worked the best. Utilizing everything we learned from both HX0 and HX1, we went forward with our final design, HX2. HX2, as you can see over here on the left, was made out of 836 carbon steel for both the shell and the tube material. The tube structure shown here inside is actually finned, as you can see on top over there. Weighing close to 84 pounds, being made of 11 gauge steel, HX2 proved to be the most beneficial heat exchanger, even though it was heavier. The areas in it, the tube and the shell areas, are close to equal, so we had the most effective heat transfer. We also designed it to be kiln compatible with the testing unit at KBR Wyland. Fabrication for all the heat exchangers was done at Houston Custom Metalworks, where we used a water jet, MIG welder, bandsaw, angle grinder, sanding discs, and various other small metalworking tools to fabricate them all. For HX2, our final one, fabrication took just shy of 60 hours. Here's an image of HX2 right before testing. The tube channels coming out of the corner plugged directly into a powerful kiln at KBR Wylie, where we ran our high temperature test. To talk more about our test is Alejandro Ruiz.
Thank you, Shen. So how did we test our prototypes? For our HX0 and our HX1, we utilized 44mm computer case fans. These fans also provided the required constraint of the low flow rate of 20 SLPMs. For our final design, the HX2 at KBR Wylie, we utilized a 66mm duct fan that was connected to a potentiometer that regulated the airflow of the required 20 SLPMs. For our heat source, we used a heat gun that allowed us to reach temperatures up to 500 degrees Celsius. So it wasn't quite the required 800 degrees Celsius, but it was enough to gather enough information and collect data. For the HX2 at KBR Wylie, we used a kiln, like Shan mentioned, that produced the temperatures up to 800 degrees Celsius. To record our temperature, we used high temperature thermocouples, Omega Type K, at our inlets and outlets of our prototypes. And we also utilized ceramic fiber insulation to minimize the heat loss to the environment of the heat exchangers. So to analyze our data, we use National Instruments Instant DAQ to record our data of the heat exchangers. It allowed us to connect the thermocouples to our laptops and record from the beginning to end of each test run. But then when we ran our final design heat exchanger test run, we used a software known as PC-based MX100 by Yokogawa Electric, and that allowed us to insert more thermocouples and more areas to get even more accurate data. With this data, we then built a calculator on Excel to calculate our overall heat transfer coefficient of all three of our heat exchangers. We also utilized MATLAB to calculate different fluid properties of air at different temperatures. So as you can see from our final results analysis, each modification we did to our heat exchanger greatly improved their efficiency. So if you pay attention to the HX1, you can see how Shan was mentioning earlier. Every time we removed baffles, it improved the efficiency of the heat exchanger. So you can see how the overall heat transfer coefficient increased with our calculations. Comparing our HX2 to the other design iterations, you can see it had the greatest overall heat transfer coefficient of 0.159, and that's using carbon steel, whereas our first one was using copper, which you would think probably it gives a better heat transfer, but the modifications we did from like area normalization and all that greatly improved our design. The inlet of our final heat exchanger was at 25 degrees Celsius, and the outlets we were testing at 205, almost 210, around there, degrees Celsius. So that was a temperature difference of a little bit over 180 degrees Celsius. So you can see that this proved that our modifications that we did to our design All the adjustments proved to be appropriate and accurate. But while we were testing and designing, we also had to take into consideration our cost constraints and the future outlook of our heat exchangers. And to talk more about that, it's Tyler Young. Thank you, Alex.
So our funds were spent according to 3 phases, starting with research and development and ending with the fabrication phase. Majority of our funding, of course, went to the fabrication phase because that required special machining, and we have custom parts on, especially our final prototype. We have several components of that require custom water jet cutting and welding, and we could refine our fabrication process further, not only to improve the heat exchanger build, but also to lower costs on those parts that required customization. So as we started off with our initial heat exchanger, HX0 here. The idea was to just get airflow running through that. So as you can see, there wasn't as much fabrication as the 2 prototypes that followed that. You can actually see masking tape here trying to seal it off to get airflow running correctly through that. And with HX2 is a similar situation, not as much material spent on that. That one was more meant for temperature, for testing for temperature to get our proper readings there. And then lastly, we have our HX2 prototype, which has extensive amount of welding and machining here, which was done at Houston Metalworks. You can see on the chart here where fabrication on the HX2 was much greater than HX0 and HX1. So if we were to take the HX2, our final prototype, and manufacture 1,000 units of that, we believe we could reduce the cost of a single unit down to roughly $375. And that would, of course, come through refining our manufacturing process, possibly using robotic instruments to have more accurate welding and more accurate water jet cutting. We only went through 1 run of this, you see, so repeating that process many times would require much quicker processes. And of course, the materials would be reduced through just buying carbon steel in bulk would reduce the cost per foot squared. So when it comes to economic feasibility, as I stated earlier, we think this is extremely feasible through not only through getting lower costs for material accumulation, but also through a better manufacturing process. And at the end of the day, we expect that you would gain back the cost of the heat exchanger, the final prototype. Of course, you would gain back the cost of that in about 2.5 years time. And this is calculated based on energy costs in developing countries I think we did it at about 49 cents per kilowatt hour. And so in the US, it's not as applicable for terrestrial applications, as we have much lower power costs. I think it's about 10 cents per kilowatt hour here. So it's extremely valuable to developing countries and remote areas that are difficult to get to traveling, and they don't have access roads or anything like that. And of course, our heat exchanger is on a smaller scale, so it's much easier to transport that. In conclusion, we had 3 functioning prototypes here. We achieved pretty much all of our design goals with each prototype, but we significantly improved as we went on for each one. And and as it turns out, we're going to end up giving our last heat exchanger over to a company that actually designed one similar to ours, and they're going to run tests on it themselves. So we think we did a really good job there. And And lastly, one of the main things that pushed our design, each design was, initially it was on paper that we were designing the initial heat exchanger, but after testing, the following designs were greatly improved, and it was mainly testing that encouraged the next steps that we would make. So we'd like to thank, we had a NASA mentor, John Groff, who started us on this project and introduced us to several people who helped us out, especially KVR Wiley. Our professors, Dr. Garcia and Dr. Rizwaz, who grilled us quite a bit following up to the presentation. And of course, we had access to Houston Metal Works, and there's KVR Wiley. And we'd like to open the floor for questions.
Thank you.
Thank you.
In terms of like finding out that you said HX2 is the best one you find out in comparison. So what is the parameter? You said like overall heat transfer coefficient. That is the only parameter you look at in terms of comparison, or any other parameter you look at?
The temperature difference we're getting. So if you look at the chart, our temperature difference for initial one was only, can you go back to the slide?
There is a high temperature. It can
Yeah, so for our shell, this one right here, we were only getting, you can see like 26 in the shell side. So we were pumping in about 150 degrees Celsius, and it was only exchanging like around 25. Our last one, I mean, we were pumping in a higher temperature, but we were getting almost 190 degrees temperature difference, 200 degree temperature difference.
The reason we were looking for just temperature is because the whole point of the heat exchanger is to preheat the air and save on power for the heater. So if we have 25 degrees Celsius air coming in and 200 coming out, that's 180 that the heater doesn't have to heat up. And that's power. Power is money. Over time, it ends up saving a lot.
These two parameters only looked at, or any other parameter?
Yeah, these are, our designs were based off of these two parameters.
Another parameter we did look at was size. We were told by Dr. Groff that ideally try to make it so you can put it on the back of a truck for the whole CTM system, and drive out to a remote location where people need oxygen and start producing oxygen there.
Yes,
So our final model does weigh about 84 pounds, but you saw I was able to carry it easily, even though that is on the heavier side. That's still man transportable.
So size is, and then another could be like the weight also, another factor could be, right?
Yeah,
Right, of course.
as
yeah.
well as changing the material. So we used, like he said, 836 carbon steel for the tubes and the shell. If we had a larger fund or a more funds and more time, we could have actually manufactured better material, not manufactured, but bought better materials for the tubes, such as silicon carbide or maybe like a higher copper that withstands the higher temperatures. We were able to find that because most of it becomes really malleable around 700 degrees Celsius.
To add on.
Yeah. Oh no, so yeah, so that's why we kind of stood away from copper, which would have made it like a lot more lightweight.
To add on to that, this application was both for space and terrestrial. So like imagine a habitat on Mars where you need to constantly produce oxygen and money isn't an issue for NASA. So you wouldn't make it out of carbon steel. You would make it out of space steel, like he says, the silicon carbide.
Or like a ceramic shell.
Something more expensive
Something that doesn't oxidize.
has way higher thermal conductivity. I mean, with carbon steel, we were able to get 180 delta T. With a higher thermally conductive metal, the numbers could be so much higher.
So then you look at the temperature difference. What about the pressure difference? Did you look at that one?
We did test our pressure difference on our first ones and realized we had a good enough pressure drop with the design. With the second pressure one, we were able to get air throughout the whole system, which kind of notified us that the pressure drop was appropriate for what we needed, especially at the 20 SLPMs, which was a big constraint for the whole system CTM.
At the end, thermal, whenever you say like made this heat exchanger, then overall heat transfer coefficient you look at that is good, as well as like overall efficiency, thermal efficiency on this. Did you have a chance to look at like overall efficiency, that this one is better than other one?
I don't think we didn't calculate the efficiency of heat exchanger.
That is also another parameter.
Yeah, that we
that also
consider.
play a big role, right?
Yeah, absolutely. But I don't think we considered the overall efficiency.
And then on the maintenance side, also another thing, like when you say a heat exchanger, which has you have the arrangement with shell and tube, and then it has so many drains, and you know the water, it comes with so much scales and so many things, and over the years you need to clean it, otherwise it will be jammed. So did you have a chance to look at that aspect?
For the designing portion, the filters, well, not just that, but we made it to be sort of modular, where you can take the top off and you can see everything inside.
Okay.
The hot side is sealed off by welds from the cold side. So also the reason we got rid of the bends was exactly because of that, because it would be hard to mess with and hard to work around. So as I was saying, for the HX2, instead of having return bends, we have the tubes going into a return channel. Easier to clean, easier to look at, and less.
We would also look into applying an air filter on it, but for our purposes, we couldn't find any air filters that wouldn't like melt, anything like that during testing.
And then there is a big temperature drop on the heat exchanger. Then did you have a chance to look at the thermal stress that can generate inside the heat exchanger?
The thermal what?
Thermal stresses change on the metal.
No.
To
We-
like
we did
thermal
not look at
expansion.
that.
Carbon
Yeah.
steel is graded for a lot higher temperatures, so we actually did not have an issue with that. I'm pretty sure if we went to a more thermally conductive metal, we would explore those problems.
Which is another reason why we didn't go with copper, even though it has a greater thermal conductivity. It's very malleable at those temperatures. So when we decided to go with carbon steel, we had more of it. It was cheaper, and then it allows the stress. It doesn't give out as much stress or become malleable at those temperatures. I mean, the melting point of that is like 1600 degrees Fahrenheit.
That doesn't mean that it wasn't deformed. If you look at HX2 over there, it looks black, it looks like scarred. Before testing, it was shiny, clean, carbon steel. We had made it so it was perfectly smooth. After running tests on it with 800 degrees Celsius air, it turned out looking like that, battle scar, but it's still functioning.
How many tests have you done?
3?
We had 3 separate tests.
Three.
2 low temperature tests at KBR Wiley, and then 1 high temperature test. The high temperature test reached about 750 degrees, nearly 800, and the 2 low temperature tests both lasted about 3 hours. Each time we were at the 300 to 400 degrees mark.
Yeah, the HX1 we did around 6 or 7 tests that we ran on that one. That helped us decide our final design.
We've actually donated HX0. We've donated HX0 to the school, so Dr. Biswas can continue doing testing with students on it. Like we're saying, they all function. It's just a matter of how well.
What do you use to measure the temperature?
Thermocouples.
Thermocouples for pretty much all of them, yeah. High temperature thermocouples at KBR for HX2. For HX0, we use the thermocouples provided by the university. Any more questions?
Is there a reason why one is longer than the other on the?
Just fabrication purposes. Like I said, when we put it, even though you design something to fit within so much tolerance, once you actually do it, maybe the manufacturer has a weird problem and it doesn't fit properly. You have to make some
It's also a product of doing this by hand in a lot of ways, which is an area we could definitely improve on.
Sure. Are you asking specifically for the reason why this top and bottom is
Yeah.
split?
Right, yeah, that's
This is
right.
actually to fit in the manifold too. Both of these sections go into the manifold, and as you can see, we have a hole over here for the shell sides. So this is to make sure that the tubes do not come in contact, that air flows correctly in the shell over the tubes and not into the tubes themselves.
Yes, sir.
What motivated you to pick this project?
we
Let's
really wanted
let's make air.
we really wanted to do
How'd you pick it?
It was a NASA project. We
Yeah.
looked at it and we thought that it's a good application. We're all in thermal fluids and thermodynamics, and we figured that this would be a good challenge.
Dr.
And what-
Biswas also recommended it because it incorporated.
I don't recommend. I made him do it.
He made us do it because it has a lot to do with thermal fluid design, things that we've already been studying prior, and we would be able to apply all that knowledge we learned from him onto our project.
Dr. Beach was at that capacity of suggesting something with a must do.
Like everything.
We are very grateful. We loved it, every part of it,
That's a
every
good
headache,
challenge.
every twist.
Right.
Oh yeah. Any other questions?
Thank you guys again for
Thank you.
listening.